Welcome back to Practical PyTorch. You move data to the GPU with .to device. That crossing has a real cost, but two loop fears people repeat are mostly myths, so we measure both on a real GPU. Every number comes from one NVIDIA L4. The bus between your CPU and your GPU is the slowest link in the machine. It is much slower than the GPU's own math. That part is true, and we will measure it. But two scary stories get repeated a lot. One, that a loop re-uploads the model every step. Two, that a per-step sync is expensive. Both are mostly myths until you measure, so we measure and let the numbers decide. First, what crossing the bus really costs, and how pinned memory speeds it up. Then we put both loop fears on the clock. This video has 3 parts. First, the bus is slow. We measure how much bandwidth a transfer really gets. Second, pinned memory. Pinned memory and non-blocking help a transfer cross faster. Third, measure the loop. We put the 2 fears people warn about on the clock. Part 1. The bus is slow. Let's measure what one transfer really gets. This is the host. That is your CPU side of the machine. The data starts here, in host RAM. To reach the GPU, it must cross this bus. This is the slow link. We measured that crossing at about 12.3 gigabytes per second. Over here is the device, the GPU itself. The data has to arrive here first, in device VRAM. Transfer bandwidth and compute throughput are 2 different speeds. The bus is the slow one, so a transfer is gated by the bus, not the GPU's math. Part 2. Pinned memory. A one-word change can make a transfer cross faster. First, the default way. A plain tensor lives in pageable host memory. We make a normal tensor here on the CPU. Calling .to device sends it, but the driver must stage an extra copy first. Now the pinned way. We ask for page-locked memory up front. .pin memory allocates a locked buffer for the tensor. Now .to device is one hop, and non-blocking lets the copy overlap other work. One catch. Non-blocking does nothing useful unless the source is already pinned. Read the 3 numbers. We sent the same 256 megabyte tensor 3 ways. Pageable got 4.72 gigabytes per second. Pinned jumped to 12.30. Pinned plus non-blocking was 12.33, essentially the same as pinned alone. So pinned is 2.6 times the pageable bandwidth. That is the biggest single win here from calling pinned memory. On its own, non-blocking barely moved the number. Its real payoff is overlapping the copy with compute in a real loop. Every value is from the L4 log. Part 3. Measure the loop, don't assume. Time to put the 2 fears on the clock. This is the loop a beginner writes. The model is already on the GPU. This line moves the model to the GPU every step. The fear is that it recopies every parameter across the slow bus. This line pulls the loss back to the CPU every step. The fear is that .item forces a hidden sync. We will not guess which line is slow. We measure the honest timing habit from the slow model lesson. Run the loop 4 ways, 100 steps, batch 128. Version 0 is the clean loop at 0.3102 seconds. Version 1 adds model.to device every step, 0.3192. Version 2 adds loss.item every step, 0.3079. Version 3 is both. 0.3239. All four sit near 0.31 seconds. Fixing both fears buys 1.04 times, which is noise. At this workload, neither habit sets your speed. The next two slides say why honestly. Take a parameter's memory address before the call. That is what data pointer returns. Now call model.to device, while the model is already on the GPU. Take the same parameter's address again after the call. The two addresses are equal, same memory, no copy at all. So there is no re-upload. .to device returns the same model when everything is already there. The only cost is the check itself, about 0.09 milliseconds per step. That is CPU bookkeeping, not a bus transfer. Across all 100 steps, it added 0.009 seconds. The re-upload fear is a myth. Move the model out for clean code, not for speed. .item, .cpu, and print of a tensor all pull a value back to Python. To hand back a number, the GPU must finish first. That is a synchronization. So does it cost you? Here, no. Version 2 minus version 0 was within noise. This step is GPU compute bound. The CPU is already waiting on the GPU, so a sync stalls nothing it was not already waiting for. But the sync is a real tax when the loop is launch bound. That means a tiny model, a tiny batch, many small ops. There the CPU races ahead and the sync yanks it back to wait. That regime is its own lesson later in this playlist. Why many small ops are slow. Same call, two regimes. Measure to know which one you are in. Fix 1. Move the model above the loop so it settles once. Make the running total a device tensor so it stays on the GPU. Each step adds loss.detach. The total never leaves the GPU, so no sync. One .item after the loop reads the value once. That is the only host read. Model moved once. Loss kept on the GPU, read once at the end. This is not faster on our workload, but it is cleaner and it is prepaid insurance for the day this loop turns launch bound. The cost that is always there is raw bus bandwidth. Pinned was 2.6 times pageable. It bites most on a big transfer. A busy GPU is not already hiding behind compute. The loop habits you were warned about are cheap on a compute-bound workload. The model move in the loop is a no-op, and a per-step .item stalls nothing while the GPU is busy. Measure before you optimize. The CPU to GPU bus is the slow link, about 12 gigabytes per second when pinned, 2.6 times the pageable rate. Model.to device in the loop is a no-op after the first call. Move it out for clean code, not speed. Use pin memory and non-blocking for big data transfers. That is where bandwidth bites. Hidden syncs like .item and print are cheap when the GPU is busy. They are a real tax in launch-bound loops. Measure. Your turn. A training loop calls model.to device inside the loop once per batch. What does that cost you on every iteration? Pause and think. Okay, here it is. Almost nothing. After the first call, it is a no-op. PyTorch returns the same model with no copy. It costs a fraction of a millisecond of CPU bookkeeping, not a bus transfer. The re-uploads the model fear is a myth. Move it out for clean code, not for speed. You now know what crossing the bus really costs, and you know which loop fears are myths. Next up is memory layout, strides, views, and contiguous. Two tensors can print the same and sit very differently in memory, and one of them makes the GPU crawl.